In this video, we'll discuss eigenvalues and eigenvectors. Assume we have a matrix A. If we use matrix A multiplied by a vector that is equal to a scalar multiplied by the vector, if this relationship holds, the vector x is called the eigenvector. The scalar lambda is called the eigenvalue. Let's use a 2x2 matrix as an example to see how we can calculate the eigenvectors and eigenvalues of this matrix. So let's assume the matrix A has this form. The question asks, solve x and lambda. Let's use the formula above. Ax is equal to lambda x. So let's write down A first. For x, it has to be a column vector, because otherwise you cannot do multiplications. That equals to lambda, then the column vector of x. We can expand what we have here in two linear equations. Moving what we had from the right-hand side to the left-hand side, we'll have something like this. And now we have a new matrix. There are a couple of things I want to say about this new matrix. The first is, if you look at the diagonal, it's pretty much the same as the old matrix, but the difference is you use the entries along the diagonal minus the eigenvalue. It applies to all square matrices of any size. The second thing is very important, so I'll write that down. It's something called Kramer's theorem. In one of the previous videos, you have learned the Kramer's rule. In Kramer's theorem, it states for a linear system to have non-trivial solution. That is, x is not equal to 0. Then the determinant of the matrix has to be equal to 0. What this tells us is the determinant of this matrix has to be equal to 0. Now, let's solve lambda. So the determinant of the matrix on the left-hand side is simply this multiplied by this minus this multiplied by this. And this gives us this expression. Solving lambda, we have two values. So lambda 1 is equal to minus 1, and the lambda 2 is equal to minus 6. So for the original matrix, let me write that down. That was the original matrix. There are two eigenvalues, minus 1 and minus 6. After obtaining the eigenvalues, we can calculate the eigenvectors. Let's scroll back a little bit. I hope you still remember these two linear equations. Write them down again. If we solve x1 and x2, we are obtaining the eigenvectors. Here, we have two scenarios. In the first case, for lambda equals to minus 1, we'll have this new expression. If we solve x1 and x2, we'll have x1 equals to 1 and x2 equals to 2. So the eigenvector we have when lambda, the eigenvalue, is equal to minus 1, is 1 and 2. In the second case, for lambda equals to minus 6, substituting this value into those two linear equations, we'll have, solving the new x1 and x2, we'll have something like this. So the second eigenvector we have is 2 and minus 1. What this tells us is in this specific matrix, there are two eigenvalues and there are two eigenvectors. The example we just covered here is a relatively simple example. In the next video, we'll go through a number of uncommon cases when you try to solve the eigenvectors and eigenvalues of a matrix.